First of all, good evening to all. Respected sir, I have uploaded an CA assignment. My topic is transmission line equation. My subject name is electromagnetic waves and transmission lines. Subject code is 23EC401. My self version, I am from department ECE. I am currently pursuing in second BTech second semester as during the 25-26 academic year in studying in Srinivasa Ramanujan Institute of Technology. My topic is transmission line equations. Introduction to transmission line equation. Transmission line equation describes the voltage and current behavior along a transmission line. These equations are essential for analyzing high frequency signal propagation. They help predict how signals are transmitted, reflected, and attenuated along the line. Transmission line equations. A typical engineering problem involves the transmission of a signal from a generator to load, generator to unload, parallel wire and coaxial cables, generator, transmission line, load. These are essential high frequency signal propagations. Basic concepts of transmission line. A transmission line is specialized or other structure design. A conduct electrical signal. Key parameters include inductance, capacitance, resistance, and conductance per unit length. The goal is to understand signal integrity and minimize lossless during transmission. Basic transmission line in equations. See the derivation and diagram. Telegraphs Telegrapher's equations overview. The telegrapher's equations are set of coupled differential equations governing voltage and current. They are derived from Kirchhoff's voltage and current laws applied to infinite essential line elements. These equations from the foundations for the analyzing transmission line behavior at high frequencies. See in the diagram and equations. Derivation of the transmission line equations. Starting with Kirchhoff's laws, differential equations, related voltage and current along the line, the inductance and capacitance per unit length determine the how signals propagate. The equations assume uniform line parameters and sinusoidal steady state conditions. See in the derivation. Voltage and current differential equations. The fundamental equations are 1 by partial V into partial x is equal to minus r plus j omega by L. 1 by fractional partial I into partial x is equal to minus z by j omega c j by 1. See in the derivation. Wave equation derivation. By differentiating the telegraph's equations, wave equations for voltage and current obtained, this second order differential equation describes wave propagation along the line. They are similar to classical wave equations with complex propagation constancy in the derivation and proof. Solutions to the wave equations. The general solution involve exponential function representing forward and backward waves. Voltage and current can be expressed as sum of these traveling waves. This solution depends on the complex propagation constant gamma. See in the derivation. Propagation constant gamma. The propagation constant gamma is equal to alpha plus beta alpha plus j by beta determine attenuation and phase shift. Alpha is the attenuation constant indicating signal loss per unit cell. Beta is the phase constant representing phase change per unit length. Propagation constant. The normalized propagation constant B is equal to n square minus n2 square by n1 square minus n2 square. N square is equal to n2 square plus b into n1 square minus n2 square. Empirical equations. See in the formula. Characteristic impedance Z of 0. The characteristic impedance relates voltage and current of forward traveling waves defined as Z of 0 square root of R plus J omega J by omega L G plus J omega C. It is key parameter for impedance matching and minimizing reflection. See in the diagram. Reflection and transmission. When a line terminated with impedance different from ZF0, reflections occur. The reflection coefficient gamma quantities the ratio of reflected to incident wave. Proper matching of impedance is reduce reflection and signal distortion. Standing wave ratio SWR. SWR measures the severity standing waves caused by reflections. It is calculated text SWR fraction 1 plus gamma 1 minus gamma. as SWR1 indicates perfect impedance matching with no reflections. Lossy versus lossless lines. Lossy lines assume R is equal to 0 and G is equal to 0. Simplifying the equations, lossy lines include resistance and conductance causing attenuation and distortion. The transmission line equations adapted to account for this lossless and realistic analysis. Practical applications of transmission line equations used in designing antennas, RF circuit, and high-speed digital system critical for ensuring signal integrity in communication systems and in the development of matching network and impedance transformers. Summary of key concepts. Transmission line equations model voltage and current behavior using differential equations. Solution involves wave propagation with attenuation and phase shift consideration. Impedance matching and reflection management are vital for optimal transmission. References: Ramo, Valery, Gervais. See in the references and textbooks. Refer the textbooks in library. Thank you.